Okay, so for chapter 10, I'm going to tell you right now, your day-to-day study, your making flashcards or a study guide or something like that is going to be really important for a lot of you. This stuff is not difficult, it's just new, and it's because it's new, poses some problems. There's two major concepts in the chapter that are not conflicting, but they are so similar, you're not going to be able to tell the difference unless you practice telling the difference starting today. So, ask questions. If your question is a what-if question, I can tell you that it's going to be wrong. Or a yeah, but question, those are not what we're talking about. It means you're not reading the question carefully. You need to pay attention to what's being asked. All right? So we're going to start right now. We're going to look at, we got these clothing pieces here. My sister used to have this book with pictures of people, but it would be just like the arm, the head, and that was about it that you could see. And then you would pick up these plastic pieces of clothing, and it would just lay right on, and you could mix and match them. And Christo knows what I'm talking about. Who cares? That's what I used to think. This is fun. You're sitting there pulling the clothes off, putting them. What is that? Who cares? But here's the deal. You got 3 different shirts here. You might call them tops. And you've got 4 different shoe choices. And you've got 2 different pairs of pants to choose. And you can make all these outfits for your character. You can use the yellow top with the gray pants, and you can put the sneakers on them. How fun would that be? If you want, you could do the yellow top. Maybe you want the blue pants. Doesn't that look good? See how the yellow button ties right into the blue? This is so much fun. Hey, Elise is thinking this is the greatest math class I've ever been in. We're talking about fashion. And Scott's over here thinking, who cares? I don't care. You know what I care about? Not that there's all these different outfits. I want to know how many different outfits. Not what they are, because I don't care. I don't care if they match or don't match. I don't care if she puts these boots with these pants. Good luck with that. All right? It doesn't matter to me what the outfit is. What matters is how many. And that's what we're going to be talking about today. We'll come back to how many. Okay? These guys all got together one afternoon and they decided we're going to go for a race. We're going to have a race. One time around the track. What's this? Orangutan. Stone-faced guy. Who's this? Farmer guy. And turkey. One of the dumbest animals on the planet. Turkey might have issues finishing the race because it goes around in the track. They may go on the straight and then get distracted and keep going. So they may never finish. Stone-faced guy. Oh no, he has Jedi powers. Today's National Star Wars Day. May the 4th be with you. What the heck? Wow. I'm just saying. I didn't invent it. Alright? Orangutan guy's pretty fast. He's got the long arms, just does this. We're going to have a race. Does it matter who finishes first? Yeah, it's a race. It's a race. This isn't about getting the medal just because you competed. This is about coming in first. And what we're going to want to figure out is how many ways are there for these guys to finish the race? What order? Okay, we're going to come back. We'll talk about that. There's 4 things for today. We didn't get to everything second period, our first period. Hopefully, you guys, we got really bogged down on the idea behind permutations. And it's really important that we spend time on it if you're not understanding it. So these are the 4 things for today. Fundamental counting principle, factorials, permutations, and distinguishable permutations. Those are the four things we want to walk away with today. Fundamental counting principle, factorials, permutations, distinguishable permutations. First thing we'll talk about is a permutation, which we're talking about a situation where you're arranging things where the order does matter. We're going to arrange things where the order does matter. That's what a permutation is. Order does matter. Give me an example of something where you're arranging things and the order in which you arrange them makes a difference. If you're arranging things in alphabetical order. If you're arranging things by height. But let's be more specific. Like people by height. The people in this room specifically by height.
People by age.
People by age. Let's move away from people. Give me some other different examples. So again, that would be the same as the height and the alphabetical, that kind of thing. You have a bunch of fossils, you want to arrange them from oldest to newest. What else? Animals by size, that would be height. We're animals by size. What about car dealerships? You're not being very specific at all. I need to know what's the group and how you're arranging them.
They each have a car, like they arrange together.
Okay. Not sure what we're talking about there, but let's assume
I don't know.
you need a specific group and how they're being arranged. What about them? Who are you arranging? What are we arranging? What's the group of things you're arranging? Okay. 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 We're all talking about things that have a measurement attached to them. Move away from those. Move away from things that you have a measurement attached to. Okay? How you finish first, second, third, fourth. What else?
Order of like colored balls pull out of the bag.
Okay? So the order in which you pull the colored balls out of a bag. What else? Yeah, we got that one. Okay? Those are all good examples of what a permutation is. Order matters. The fundamental counting principle is a way to determine how many different ways you can arrange a group of objects. And there's, with the fundamental counting principle, if you're going to take n objects and you have n exclamation point ways to arrange those n objects. This exclamation point, something new for us. It's called a factorial. So when you see n exclamation point, it's red, n factorial. Mathematically, a factorial is telling you n factorial equals whatever n is, times 1 less than n minus 1, times 2 less, n minus 2, times 3 less, all the way down to times 3, times 2, times 1. So for example, 5 factorial is 5 times 4 times 3 times 2 times 1 is 120. Now, one of the ways that we use the fundamental counting principle is to set up, and I'm going to actually have you set up a number of boxes. Now, the number of boxes is for how many things you're actually, how many places are you arranging? Not necessarily how many things are we arranging. But how many, in this case, when we do 5 factorial, we have 5 times 4 times 3 times 2 times 1. In the first spot, there are 5 choices. Once you've filled the first spot, how many choices are left for the second spot? 4. And how many for the third spot? 3, then 2, and then finally you only have 1 for the last spot. If you multiply the numbers in the box, that's how the fundamental counting principle is going to work for you. 5 times 4 times 3 times 2 times 1 is 120 ways. Now, if we go back to our race with orangutan, stoneface, farmer guy, and turkey, how many places are there for the race? 4. We have 4 places because there's only 4 contestants. So we separate into 4 boxes. How many choices do you have for the 4 boxes? For the first spot in the race, 4. Second spot, in 1. That would be 4 factorial, and 4 factorial is 24 different race outcomes. 24 different race outcomes. Now let's go back here. Again, I don't care what the combination of outfits is for this. Spencer, do you care? You don't sit at home wondering, does this top and oh, I wore this with this the other day and I need to have a different color. No, we don't care. How many different boxes do I need for these outfits? How many different boxes do I need to figure out my outfits? How many? 3. Why? There's tops, there's pants, oops, and there's shoes. That's how many boxes we're choosing. How many choices do I have for the top? 3. How many choices do I have for the pants? And the shoes? So how many different outfits can we make? 24 outfits. Oh my goodness. It's fantastic. I can come to school every day for 24 days with a new outfit on. This is going to be so much fun. Right, Elise? Can't wait. Everybody follow what we're doing here. It's not what are the outfits, it's how many outfits. Now, you may have learned this in your middle school class. You have, in your choices, you have the yellow shirt, you have the striped shirt, and a green shirt, right? And you have the gray boots, the red boots, the high heels, and the sneakers as shoe choices. And then you have the blue pants or the gray pants. And if you follow the tree branches, it tells you exactly what the outcomes are. I can wear the yellow top with the gray pants, yellow top with the gray boots and the blue pants. I can wear the yellow top with the gray boots and the gray pants. Those are 2 different outcomes. I can wear the yellow boots or the yellow top, red boots, and the blue pants. Yellow top, red boots. No, we can go through that. We don't care. We only care how many, and that number is 24. The tree diagrams are good if you want to know what the outcomes are, but not if you want to know how many. They take days to do. Okay, so fundamental counting principle can be very useful when you're arranging or trying to figure out how many objects there are in the arrangements. Permutation, keep asking yourself, especially in your homework tonight and as you go through, does the order matter? If the answer is yes, it's a permutation. Now clearly tonight everything should be yes, but you should understand that it's yes and you should understand why. So the order matters. First place, second place, third place. President, vice president, treasurer. You don't think order matters? Think about Barack as the treasurer. Think he would feel like he's got the same amount of power? I don't think so. And remember we talked about factorials. We can set up here's a couple of examples with phone numbers. So the phone number is going to be 791 and then 4 more digits. Okay? 791, first 3 digits, and then 4 more digits. There's 2 ways that we can ask the question. You could say with repetition or with no repetition. You need to understand if it does not say no repeating, then that means you can repeat. It has to absolutely say without repetition of numbers in order for you to say no repeats. Now, this is a bit of a tricky question. Does the 791 figure into the with and without repeats? And I would say it's not very clear. I'd say it's very ambiguous whether that's true or not true. How many different numbers can be generated? Well, if we're going to say repetition of the next 4 digits, technically we could say that there are 7 boxes. How many choices do you have for the first number in the box? 1. How many choices for the second number? 1. How many choices for the third number? Now this isn't meant to be a trick, but you need to think before you answer this question. We're putting a digit here. How many choices do you have for the 4th spot in this number? 10. The number of digits that we have are the numbers 1 through 9, those are digits, and 0. 0 is a digit. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 0 could be a number and a phone number. You have 10 choices here. How many choices do you have for this spot? 10. Here, 10. And 10. How many phone numbers can we create that start with 791? This is where you need your calculator for some of you. And you're going to multiply these all together, and you're going to get 10,000. So there are 10,000 possible phone numbers that start with 791. Now, if I tell you that we're going to do the same problem without repetition in the entire phone number, let's assume we're talking about no repeating in the entire phone number. We set up our 7 boxes. Okay, we set up the entire 7 boxes, and it's still going to be 1, 1, 1. Now here's where it's tricky. What is the number that goes in the 4th box? 7. Because we've already used up 3 of our numbers technically. 7, 9, and 1. We can't choose those digits. How many digits are left to choose for the 5th spot? 6, 5, and 4. When you multiply these all together, how much do you get? Does everybody follow that? This is a little bit tricky with the with repeat and without repeat. Elise?
Why are there ones in front of other numbers?
Well, the number is going to start 791. How many choices do I have for the first number that I dial? Okay, the numbers that I'm going to dial are 791 and then 4 more numbers.
Okay.
So the first number I push on the phone is going to be, how many choices do I have for the first number?
Without it.
No, I'm going to dial a phone number. What's the first number I'm going to push?
7.
How many choices did I have for that first number?
9.
What's the first number?
7.
Is there any doubt what the first number is? How many choices do you have?
1.
It's got to be a 7. What's the second number have to be?
9.
How many choices do you have?
1.
Only 1. It's the 9.
Okay.
Does that make sense?
Yeah.
This stuff is tricky, so make sure when you're not understanding what we're putting in the boxes, don't sit there and say, I should know this. You shouldn't. It's not intuitive. So you have to keep hammering with questions till you get it. Otherwise, the quiz and the test gets really nasty.
So one of the text box, the first one you did, that was you can do it with repetition.
So you can have the number 791-7777. 791-1111. This one is saying that on the phone number, no digit can be repeated at all. So that means 791, 7, 9, and 1 are already used. So I have to pick from the other 7 digits, then 6 digits, then 5, then 4. And there's only 840 phone numbers that we can create that way. Not going to work. Everybody follow that? This is the fundamental counting principle. Okay? Go here. This is fundamental counting principle. You're going to go to a restaurant and you decide that you really like this restaurant, and you said they have a menu with 5 appetizers, 6 main meals, 9 salads, and 3 desserts. And you really like it. You know the owners, the waitresses all know you, and you say, I'm coming here every single day for dinner until I have to order the same meal that I've already had. So I want to know, how many days can I go without ordering the same meal? I'm only coming for dinner. So we have the appetizers, we have the main course, we have the salads, and we have the desserts. So there's 4 boxes, because those are the 4 categories we're trying to choose from. How many choices do I have for the appetizers? 5. And for main meals and salads, 9, and desserts, 3. And when you multiply all of those together, 810, that means you can go to this restaurant for 810 straight days and never once have the same meal as a repeat. How exciting. You better love this restaurant. That's all I can say. That's like 2.5 years, right? Yeah. No, we're only going for dinner. Only going for dinner. Okay? Now, here's an example. Blood type. What's your blood type? If you know your blood type, raise your hand. 5, 6 people, that's it? Wow. If you need blood, I'm a universal donor. You can come to me. Okay? O positive. What are you? O negative. So we've got everyone covered here. What else we got? What are you? B positive? AB. AB, ooh. Ooh, not the most rare, but pretty rare. Any AB negatives in here?
Positive.
You're positive that you're not
No, I'm
AB?
AB positive.
So we have 3 AB positives. That's pretty amazing. All right, so there are 4 types of blood, A, B, AB, and O. And each blood type has an RH factor of plus or minus, positive, negative. And then you could have male or female. I wasn't aware that made a difference. Imagine going into emergency. Is that male blood you're giving me or female blood? I didn't know there was a difference. And please don't put that female blood in me, because I'm going to come out indecisive and wanting to go shopping. What good is that? How many boxes do I need for the total blood, including the male and female? Paige? Each group of things that you're choosing from, we're going to choose one from the AB, and O. We're going to choose one from the plus minus, and we got to choose one from the male or female. Okay? RH, and this is the gender. I'd like you to label the boxes on ones like this. You don't need to do it for one like a phone number, but for one like this, just label. How many types are there? 4. How many RH factors? And genders? Usually 2. Altogether, the total number of blood types we have? 16. 16 different blood types. And it's not what they are that I care about, it's how many there are. We're headed for probability. And probability is dependent upon how many choices do you have. So what's the probability of? Then we'll get to that. Everybody good on this example? Fundamental counting principle. Pretty easy. See if you can do the pizza one. So our 4 boxes. You're going to have crust, meat, cheese, and veggies. Who's putting veggies on this?
So good.
Yeah. So how many different crusts do we have? How many different meats?
5.
Cheese?
8.
And 8. And as far as me, nothing is going here. Okay? I don't do that. I would prefer just a plain old cheese pizza.
Vegetarian?
I don't eat certain meats. Yeah. It's a personal
Wait, and you
choice.
don't put veggies on your pizza?
No.
That's not normal.
I like plain cheese pizza. I eat a lot of fish and a little bit of chicken. I can't chew the not at all. Not for 25 plus years. Sorry. So 3 times 5 times 4 times 8. So we can get a lot of pizzas made if you're willing to go with the 8 veggies. A lot of different pizzas. I can't imagine they'll all be good, but there you go. So to get into your house, to get into your gated community, 4-digit code. Now the digits that they're telling you can choose from are 0, 1, 2, 3, and 4. How many codes are possible if you allow repeats and if you don't allow repeats? Be careful with this. It's a 4-digit code, right? When we allow repeats, how many choices do you have for the first digit? Be careful. 5. This problem is saying you have to choose from these digits, and there are only 5 to choose from. So when we're repeating, the second spot is 5, 5, and 5. So altogether, 625 different codes that we could create.
Why did you put 5?
Because we can repeat. I could have the code 0000. Do you understand why there's 5?
Yeah, because you can repeat all of them.
Well, repeating just means you can repeat. I'm not saying you either can or can't repeat. It's a pregnancy question. You either are or you aren't. You can't kind of sort of repeat. Like you can't be kind of pregnant. It's a yes-no question. Do you agree with that? Repeating is a yes-no. You're either allowing repeating or no repeating. There's 5 to choose from. I can choose any of the 5 numbers in any of the spots when we repeat.
But how did you know repeat?
It says you can repeat. It's a dead giveaway. Okay? Now, with that kind of sarcastic response from me, if it's better for you to look at it this way, in order for you not to repeat, they have to say it. Because in this right here, if I don't give you this, I just say how many codes are possible. And I cover this up. How many codes are possible? There's nothing that suggests we can't repeat. You have to allow repeating.
That's what I meant.
Does that make sense? And
Didn't say like
if you don't flat out see no repeating allowed, then you have to assume they're allowing repeating. Well, again, different codes can be repeating. 5252 is different from 2525, right? Same numbers, but the order matters. This is a permutation. Now, do we allow repeating? You bet. But if I say no repeating, I can't do 5252.
So if it wasn't repeated or not repeated,
You have to assume it's repeating. So we have to say no to repeats, and it has to be crystal clear. Okay? So if we no repeat, 5 in the first spot, how many in the second spot? 4, 3, 2, all together, only 120 possible codes if you don't allow repeating. Does this make sense to everybody? Again, the questions you want to keep asking are the ones you've been asking. Can I repeat? How can I tell from the question? If you're not sure, you have to keep asking that question of me. And don't feel like, well, everybody's asking the same question over and over again. You have to make sure you get it. How many boxes? How much goes in each box? You want to make sure you're crystal clear on these things. California license plates. 1 number, 3 letters, followed by 3 numbers. If we do this with repeating and without repeating, again, we're just trying to cover our bases. How many choices with repeating for the first spot? 10, thank you. Second spot. Wow, that wasn't much confidence. Where's my English people? 26 letters here in America. 26. We're not using the Hawaiian alphabet. Don't say what if. What if we were in Hawaii? We're not. We're here in the real America. Right. But you can't believe the questions I get. Next spot, 5th spot. Back to 10, 10, and 10. Gotta have your calculator to get this mess. How many 10 times 26 times 26 times 26 times, so it's 10,000 times 26 cubed.
17576 with 4 zeros.
Big old number. A lot of different license plates. 175 million different license plates. 175 million. We're going to run out. We're all going to run out. Okay? Anyone have a new car at their house? In the last 2 years? What's the first digit on your license plate? Do you know? You don't have a license, so yours is really new. A what? 6. That means we only can go 7, 8, and 9, and we're done. You'd be surprised, because I had a car that had a 2 on the front. Back in 91, my license plate was a 2X, so almost a 3. So we've gone to 6 in 20 years. We're going to be 20 more years in your lifetime. We're going to run out.
Can't they just add a digit or change?
Absolutely. They have 2 options. They have 2 options on what. How many in the first spot? 10. Be careful. Second spot. 3rd spot. Good. 24. 9. Very good. So when you can't repeat, we can still choose from all 26 letters, and then it's 25, 24. And we already chose a number in the first spot that can't be repeated here in the 5th spot. How many different license plates now?
17,624,000.
Missed the first part. Only 78? So 78 million. Less than half of what we had before. can do the same thing. But New York is letter, 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 followed by number, 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 number. So in the first spot when we repeat, 26, and then, and is it going to change what happened from the numbers in California? Are we going to get a different total? No, it's going to be the same total, but it's a different order or arrangement. So this would, as somebody pointed out, this would give California a whole new set of license plates, a whole new 175 million license plates. And I don't know what they're going to do. I have no idea, but I'm sure they have a plan. I'm sure they have a plan. Okay, and down here, when you can't repeat 26, 25, 24, and then 10, 9, 8, 7, which again, same as California, just in a different permutation, different order. Okay, so we have two situations here. The evening news, there's 8 stories that are going to be presented. If you're going to present all 8 stories, how many ways can you do that? 2 words to answer this question. If you're going to present all 8 stories, how many ways can we present them on the news? No. Correct, but I'm looking for how many in 2 words. 8 factorial, very good. 8 factorial. If you're presenting them all, it's going to be 8 factorial. If you forget that it's 8 factorial, you think about it as a race. And how many choices do you have for the first spot in the race? 8. Second spot? 6, 5, 4, 3, 2, 1, which you're going to multiply together, better known as 8 factorial. Now, the reality is you're not going to get all 8 stories in the news tonight. You're only going to be able to use 3 of them because we've got to do the sports, we've got to do the weather, we've got to do the this, that, and the other thing. When you're going to choose some of the stories, we're going to use the NPR formula. What's NPR? National Public Radio. So we're going to use the National Public Radio formula, which is going to be n factorial over n minus r factorial. Here's the breakdown of the parts. N is the total number of available that you're choosing from. And R is how many of the group do you want. And again, key component here, order matters. Which story comes first in the news matters. NPR, how many to choose from? That's N. R is how many you're choosing. N factorial over N minus R factorial. N factorial over N minus R factorial. So when we go to the story, this is what I expect to see from you. You need to know that it's a permutation problem because, again, the order matters. There are 8 stories to choose from. How many do we want to choose? 3. 8 permutations taken 3 at a time. 8 taken 3 at a time will be 8 factorial over 8 minus 3 factorial. Eight factorial, 8 minus 3 factorial is going to be 8 factorial over 5 factorial. That's not going to be 3 factorial. Okay? 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 5 factorial is 5 times 4 times 3 times 2 times 1. What cross cancels?
1, 2, 3, 4.
Yeah, the 1, the 2, the 3, the 4, and the 5. So these cancel, 3s, 2s, and 1s, leaving us with 8 times 7 times 6, which is 336. Now remember, fundamental counting principle, it's like a race. How many stories? 3. How many to choose from in the first spot? 8. Second spot? Which is exactly what we got right here. What's the point of this?
Yeah.
Because this is how you can do this with a permutation formula. This will make a lot more sense when we get to the next part of this chapter. So not only, I mean, you're looking at just one example so far. There are other things that we're going to do with this. All right? So, great question. No need to use it, but the formula is there for us. Yes? Yep, we'll talk about them later. Because what happened last period is people started looking at their calculator and they missed the whole lesson. Oh, I found it! It was 9:10. Missed everything else. Waste. This is the number of permutations of 8 items taken 3 at a time. Your formula is the NPR formula, 8 factorial over 8 minus 3 factorial. You circle it. That's how many ways that we can present the units. We're doing it right here. This 8p3 means 8 factorial over 8 minus 3 factorial. 8 minus 3 is 5. 8 factorial is some big, huge number. And 5 factorial is 120. And when you divide the big number by 120, you're going to get 336. Okay? And I'm going to give you other ways to do that. And in this case, we can always use the counting principle. Bear with me when we connect these dots. So, you go to PE, you're at the gym, you have a bike, and you lock your bike up, you lock your locker up. What's the thing that you use called? It's called a combination lock. Well, I don't know if the person who invented the combination lock named it. If he did, brilliant job inventing it, but he clearly didn't take this class because an idiot job of naming it. It is not a combination lock because the order matters. A combination means the order doesn't matter. What should he have named his lock? He should have named it a permutation lock. We shouldn't be doing this with the word combination. We should be talking about a permutation lock. And every single person in here should say it's a permutation lock. And we should all be calling it a permutation lock. But because somebody didn't pass Algebra 2, they misnamed and called it a combination lock. Because a combination implies that 3, 37, 19 will open the lock. 19, 3, 37 also would open the lock. If it were a combination. They're not. They're permutations. A permutation lock. How many numbers are on your lock combination? How many?
49.
Are there really?
Yeah.
39? Isn't there a 0?
Yeah, 40.
So 40. How many choices for the first spot?
40.
40. How many for the second spot? Be careful. 40. And for the third spot? 40. There are 40 for each spot. So how many permutations are there for your lock? 64,000. And there are not 64,000 combinations. There's 64,000 permutations. They are misnamed. All right? It's not a combination lock. It's a permutation lock. We're just stuck with that name. Everybody follow that? The order on your numbers matters, right? not a combination, it's a permutation. Okay? 12 teams are in a playoff. How many ways can they finish the playoff? How many ways can the 12 teams finish? So, what do I need to show for work on that? 12 factorial. And then that's all I need to see. It's 12 factorial. And what was 12 factorial for?
479,000,1,600.
001.
Yeah. Thank you, Mary Rose. And then last three?
660.
Jeez. See, if I had women blood in me, I'd be, let's go shopping and I'd be impatient. Here we go. This is what I need. How about 3 teams finishing first, second, and third? Oh, not reading the question. It's a really ambiguous question. How many ways can 3 teams finish first, second, and third? Not the way the question's written. And again, your answers are probably good answers.
It's according to 6.
Read the question. It's part B, but read the question. Okay, the way this is worded, you have 3 teams finishing first, second, and third. How many ways? 6. Badly worded question. Very badly worded. So it needs to be something that's clear. It needs to say, you have 12 teams. How many ways can first, second, and third place finish? You know, how many ways can the 12 teams finish first, second, third place? This is really not well worded. So we can go fundamental counting principle in the first spot. 10. Again, it's not worded well, but that was really what they were after, and I know that's what most of you did. And so how much was that? 13, 20. Okay? You have 50 raffle tickets in the bucket. 4 prizes. How many ways can you get the 4 prizes drawn and distributed? 50 different tickets. Each ticket wins a different prize. Each drawn ticket wins a different prize. How many ways can we choose or give out these prizes? This is permutations of 50 items taken. How many are you choosing? 4. 4 at a time. 50 factorial, 50 minus 4 factorial. 50 factorial over 46 factorial. Or counting principle. 50, 49, 48, 47. Gives you the same thing.
Does it matter which one you choose?
For this problem, no. I need you not to throw this away just because we haven't used it without being able to do this yet. What do we get? How many?
527,000.
Okay, so about those. Now everything changes. Everything changes if the 4 prizes are the same. It is the order doesn't matter now. You don't care whether you're drawn, the ticket you have is drawn first or fourth. You get the same winning prize. But if we're going to give you the worst prize, second worst prize, third worst, and then the grand prize is last one, you want it drawn last. The order matters. What's different about these two words? What's different about the letters in these two words? The arrangements.
They're the same.
Look closely.
Oh, wait, I know.
You know, let's make this a little bit bigger.
The
Maybe
edge, the R and S's together.
That's the same thing, but
They're the same. What's that? Let's talk about the order. That's all I'm asking you. I'm not. Don't say one's a smidge bigger than the other. That's not what I'm trying to get at. We're talking about an arrangement. The order of the letters in the word swimming.
They're the same.
They're the same. Anyone see anything different about the order of the letters? Penelope, tell them what's different.
The M's are inverted.
The M's are switched. What the heck? Nope, just the M's. The M's, this M I switched and put it here, this M I switched and put it here. This went here, this went here. I don't understand why you can't see that. It's obvious, isn't it, Penelope?
Yeah,
Yeah.
they're the same.
They're not the same. I don't know why are you arguing with me, Mayrose, today? What is it? Did you not have a good breakfast? You came to school hungry and now get the abuse today. I don't understand it. Why can't you see this? It's clear that I put this M right here, and I moved this M right here.
Looks the same.
It looks the same to you? Oh, well, maybe I can, maybe you can tell them this one. Okay, so if I use these letters in swimming, and I switch my M's, whoa, get away from me there. Can you tell now? Yeah, it's easy to tell now. It's really not easy to tell here. In fact, it's indistinguishable. So even though I switch the M's, it doesn't matter because it looks exactly the same. So no real benefit from switching occurred. And you can't tell the difference. These are indistinguishable. If I switch things like the S and the W, okay, well that's kind of obvious. But now, when I make each letter look totally different than the others, when I switch letters that are the same, I can take this I and switch it with this I, and you can say, oh yeah, that's a different permutation. It's obvious the star I is now before the green I. All right, so what we're talking about here is how can we tell if it's this? It's got to be something you can tell. That's what makes it distinguishable. Distinguishable permutations. Okay? Number of distinguishable permutations of n items taken n at a time is n factorial on top. We're going to arrange them all like you can tell the difference. And then we're going to divide by the number of repeats in the factorial form. So when we use the word swimming, the I repeats how many times? Twice. And the M repeats how many times? Twice. How many letters altogether? Oh, sorry. How many letters altogether? This is just boys and girls were counting today.
6.
1,
2, 3, 4, 5, 6, 7, 8.
very good, Melinda.
Thank you.
You're counting, I'm sorry?
8, and you said we're just counting.
Right, I'm sorry, Hannah. There were a lot of people who said 6. And I just didn't know who was saying it. I think the 6s were louder than your 8. Okay? But we just want to know how many there are, boys and girls. We just count them. And see how all these little things become outrageously confusing? How many are there? Now you're second guessing yourself. Do I count 2 M's? Do I count 2 I's, or do I just count them as one letter? We want to know how many we're arranging. There's 8 of them. And that's where you get in trouble when you start second guessing yourself. So it's 8 factorial. Now, the I repeated twice. So that's a 2 factorial for the I's. and the m repeated twice times another 2 factorial for the i's. What you're doing is dividing out all the times that you just switched the m's or you just switched the i's. You're dividing out the repeats. You're dividing out the repeats. You need to be really careful when you're doing this. You can do it on a calculator, but you need to make sure that 2 factorial times 2 factorial stays in the bottom. So you have 8 times 7 times 6 times 5 times 4 times 3, 2, 1 over 2 times 2. Okay. You just got to make sure you put parentheses around the denominator. How many ways can I rearrange the words or the letters in the word swimming? How many? 680? Different?
Well, it's 2 times 2.
On the bottom. 8 factorial on the top. You got something different? What'd you get?
10,080.
10,080. You're going to have, if you were working it out, it looks like this. You don't really need the 1. And then 2 times 2. Now the 2 times 2 is going to cancel with that 4. So you're going to have 8 times 7 times 6 times 5 times 3 times 2. How much? 10,080? Christy? How did you get?
It's 1,000.
Go pretty proud. 10,080. So that's what you had?
No, I had something crazy.
Bad calculator. Anyone not getting it? Right. Mississippi. See how many distinguishable permutations there are. See how many distinguishable permutations there are for Mississippi. So what do I need to see for the number of permutations over here? What should you show me? 11 factorial over 4 factorial, 4 factorial times 2 factorial. Now remember, 4 factorial is not just 4, it's 4 times 3 times 2 times 1. So it's 24, 24 and 2. Okay? So how many Mississippi? 650? 34,650 different ways to rearrange the letters in the word Mississippi that you can tell that you rearranged them. Does that make sense to everybody? That's what we mean by distinguishable permutations. What did you get?
39,960,000.
So on your denominator, did you figure out 4 factorial? So when you divide, you got to go close, open, and then close. Does that work? Super important that we can use our calculators, right? How many permutations are there for Mississippi? 2 words. 11 factorial. Then we can evaluate 11 factorial. What's 11 factorial? No, yeah, but what is it actually? The big huge G number. It's like being in church again. Thank you. A boatload. But there's a whole bunch, whatever 24 times 24 times 2 is 576, 1138 or something, 32. That's how many ways that you'd have to divide this by to figure out how many distinguishable ones there are.